everyone. I want to welcome you to this new section. In this video, I will be talking about how to identify the organic compound, the class of organic compound represented by a given mass spectrum. So in mass spectroscopy, the outcome of mass spectrometry is what we call the mass spectrum. A mass spectrum is a graph of abundance of ions against the mass to charge ratio of those ions. So in a mass spectrum, you expect that the vertical axis represents the abundance of a particular ion, most usually a cation, and the horizontal axis represents the mass to charge ratio of that particular ion. So in a mass spectrum, we always see abundance against the mass to charge ratio, and at different mass to charge ratio, you always see a signal that represents a particular ion that was formed during the ionization process in the mass spectrometer. At the same time, the signal also represents the abundance of this particular ion, which most times depends on the stability of the ion that is formed. So in this particular video, I will be discussing how to read a mass spectrum in order to be able to identify what class of organic compound the mass spectrum given to you represents. There are some key things that you can always look out for in a mass spectrum that will easily help you to know what class of organic compound a particular mass spectrum represents. And these are some of the things I'm going to be sharing with us in this particular video. But take note that things I'm going to be mentioning in this video are not the only thing you expect to see in a mass spectrum. There are other signals that you also see in a mass spectrum, but these particular key points I'm going to be mentioning are things that you can easily see in a mass spectrum that will help you to easily know that this particular mass spectrum given to me represents this particular class of compound. As we know, we have different class of organic compound, but for this particular video, I'm going to be talking about this set of organic compounds and how to know a mass spectrum that identifies each of them. And I'm also at the end going to talk about mass spectrum that usually represents a nitrogen containing compound, and also how to identify a mass spectrum that identifies a compound that contains aromatic ring system. Before I'll start highlighting the key things to look out for in a mass spectrum to know which class of compound the mass spectrum given to you represents, I would also like to bring to you some key things that you also have to know pertaining to a mass spectrum, which is the parent peak and the base peak. In a mass spectrum, the parent peak is the peak, or let's say the signal that identifies the molecular ion that is formed during the ionization process of the molecule. You know, in a mass spectrometer, one of the things that takes place is ionization of the molecule that you are subjecting to the mass spectrometry. At the same time, after ionizing the molecule by bombarding it with electron to form a molecular ion, then the molecular ion undergoes several fragmentations to form different forms of ions. Some of these fragments will be cations, some of them will be neutral molecule, some of them will be radical cation. But the mass spectrometer can only identify cations that are formed as what? As fragments. So the mass spectrometer can only detect fragments that carries a positive charge. So if any fragment is formed during the process of mass spectrometry and it doesn't carry a positive charge, the mass spectrum will not produce a signal for it. So what I'm saying is that the parent peak in a mass spectrum is the signal or the peak that identifies the molecular ion, and most times and in general cases, a molecular ion has the same mass to charge ratio as the molecule itself. So it means that if I know the parent peak from a mass spectrum, I have already known the molecular mass of the given molecule, which can also maybe help me to determine the molecular formula of the given compound represented by the given mass spectrum. So note that a parent peak is a peak or a signal that identifies the molecular ion peak in the mass spectrum. The second peak that is also general for a mass spectrum is the base peak. The base peak is a signal in the mass spectrum that have the highest abundance compared to other signals that are present in the mass spectrum. So note that most times in the mass spectrum, you will have the parent peak and also the base peak. So take note of those two things, the parent peak and the base peak within a mass spectrum. Now, I'll be discussing now I'll be highlighting some of the key things to look out for in a mass spectrum to know whether the mass spectrum represents a straight chain alkane, a branch chain alkane, or either of all of these class of organic compound. For a straight chain alkane, you could or you for a straight chain alkane, the molecular ion peak can either be present or absent. And the rule is that the longer the chain of alkanes, the lower the tendency of having the parent peak being present in the mass spectrum. So it implies that long chain alkanes that are straight chain might not have a parent peak in their mass spectrum compared to a short chain alkane that is straight chain. That's what that implies. Another thing that's particular for a mass spectrum that represents a straight chain alkane is that you can always see alkyl ion peaks in a mass spectrum that represents a straight chain alkane. What do I mean by alkyl ion peak? We are talking about alkyl, we are talking about methyl, ethyl, propyl, butyl, pentyl, hexyl, etc. Each of the mentioned alkyls can always produce a signal in the mass spectrum of a straight chain alkane, although it is not all these alkyl produced as a cation that will have a prominent peak. In most cases, or generally for straight chain alkane mass spectrum, the prominent peak is always produced for propyl ion or either for a butyl ion. So now, how do I know an alkyl ion peak? Most times, the alkyl ion peak for methyl is usually at 15. For ethyl ion, the peak is at 29. For propyl ion, the peak is at 43. For butyl ion, the peak is at 57. For pentyl ion, the peak is at 71. For hexyl ion, the peak is at 85, and so on like that. So if you look at those mass to charge ratio I've mentioned for different alkyl ions, you will see that they differ by what? By 14. So and that's another feature you can always see in a mass spectrum to know if a mass spectrum represents a straight chain alkane. That is, the prominent peaks will differ by 14. So the prominent peaks in a mass spectrum that represent a straight chain alkane will always differ by 14. So you can see a peak for methyl, for ethyl, for propyl, for butyl, pentyl, hexyl, eptyl, octyl, etc. But like I said, it is not all of these signals that will be prominent. The most prominent of these alkyl ion peaks will either be for the propyl ion or for the butyl aeon, and that's how to know a mass spectrum that identifies a straight chain alkane. For a branch chain alkane, some of the properties mentioned for the straight chain alkane will also be seen for a branch chain. The major difference between the straight chain alkane and a branch chain alkane in terms of their mass spectrum is that in a mass spectrum that represents a branch chain alkane, some of the alkyl aeon peaks will be missing. So in a straight chain alkane, you expect to see a full signal for all the alkyl ions, but in a branching alkane, because of the branching within the system of that alkane, some of the alkyl ion peak will be missing. So in a mass spectrum that represents a branching alkane, you can say that some alkyl ion peaks will be missing. Unlike what you have in a straight chain alkane, where you expect to see all alkyl ions, depending on the length of that particular alkane though, in a branch chain alkane, you will not see all the alkyl ion peaks. Some of them will be missing. Another thing also is that in a branch chain alkane, the molecular aeon peak or the parent peak can also be absent or present. But comparing a straight chain alkane mass spectrum to a branch chain alkane mass spectrum, the rule is that the more branch an alkane is, the lesser the tendency to see the parent peak in the mass spectrum of that particular alkane. So that implies that a branch chain alkane would have a very low tendency of giving us the parent peak compared to a straight chain alkane. So please take note of that. Another class of compound that a mass spectrum can represent is an alkane. An alkane, for alkenes generally, especially for the terminal alkenes, for always see a prominent peak at the mass to charge ratio equals to 41. By terminal alkenes, it implies that the double bond is at the end of the given alkene. Now, but at the same time, depending on the length and the position of the double bond, this prominent peak that is usually at 41 can always change from 41 to 55, from 55 to 69. That is, you have a difference of what? Of 14. But that depends on the position of the double bond, at the same time on the length of the given alkene. Now, for aryl alkyl compounds, are compounds that contains an aromatic ring system, as this, an aromatic ring system together with an alkyl group. Now, for this class of compound, where you have a benzene ring, that is phenyl ring with the alkyl group together, for this class of compound, you can always see a prominent peak at 91. At the same time, you can also see a prominent peak at 77. Every compound that contains an aromatic ring, the mass spectrum of such compound would contain a peak at mass to charge ratio of 77. So in an aryl alkyl compound, you also expect a prominent peak at 77. For alcohols generally, if you have a mass spectrum that represents an alcohol, you always expect a peak at n-18. What this implies is that if the molecular aeon peak or the parent peak in a mass spectrum is say is probably 100. So what I'm trying to say there is that if that mass spectrum represents an alcohol, we are expect to see a peak at 82, because 100 minus 18 will give us 82. So in a mass spectrum that represents an alcohol, you should always see an M minus 18 peak, because from an alcohol we can always remove H2O and have the remaining part of the molecule as a cation, and that's how we have a peak at M minus 18. But this particular peak is only found in alcohols. Also note that we have different classes of alcohol. You can have primary alcohol, secondary alcohol, or tertiary alcohol. So there is also a way to differentiate between these three classes of alcohol. But note that for any mass spectrum that represents an alcohol, it will have a peak at M minus 18, which represents removal of water. Now for ethers, for a mass spectrum that represents an ether, in most cases, a mass spectrum that represents an alcohol and the one that represents an ether usually have similar prominent peaks. But the major difference is that a mass spectrum that represents an ether lacks the M minus 18 peak. Even though the mass spectrum of ether and that of alcohol looks similar, yet a mass spectrum that represents an ether will not have an M minus 18 peak. Also, in ether mass spectrum, alkyl ion peaks is prominent. Comparing ether and alcohol mass spectrum, both of them usually have similar peaks. For example, both alcohol and ether mass spectrum we have a prominent peak at 31, 45, 59, 70, 73, 80, 87, etc. for both alcohol and ether mass spectrum. But what makes a difference between the two of them is the peak at M minus 18. And that's how to identify the mass spectrum of an ether, at the same time to differentiate it from the mass spectrum of an alcohol. For this remaining class of compounds, which are carbonyl compounds, talk about ketone, aldehyde, carboxylic acid, and ester. All of these are carbonyl compounds. Generally, for all carbonyl compounds can undergo what we call McLavity rearrangement. Probably in the subsequent video, I will try to explain what that implies. But just know that carbonyl compounds can undergo McLavity rearrangement, and this property of carbonyl compound help us in identifying their mass spectrum, because when each of these carbonyl compound undergoes McLavity rearrangement, they produce specific signals which can be used to identify them, even though the position of their functional group also can change some of these values. For ketone, when ketone undergoes McLavity rearrangement, they produce a prominent peak at mass to charge ratio equals to 58. This peak at 58 is the basic place where you can see a signal for a ketone that undergoes McLavity rearrangement. But depending on the position of the carbonyl within the ketone compound, this value can also change. But it will change to a point whereby you are adding 14 to this 58. That is, you can have the peak for McLavity rearrangement in ketone compound to be also at 72, to be at 86, and so on like that. So due to macromatic rearrangement, the mass spectrum for a ketone or for a ketone class of organic compound, we have a prominent peak basically at 58, or depending on the position of the carbonyl functional group, you can also have it at 72, 86, and so on and so forth. For aldehyde, when aldehyde compound also undergoes macromatic rearrangement, it produces a prominent peak due to this rearrangement at 44. Now, this does not change for an aldehyde because the aldehyde functional group is usually terminal. That is, the position does not change. Unlike what you have in ketones, where the position of the functional group can always change. For aldehyde, there is also a diagnostic signal that can help us to identify a mass spectrum that represents an aldehyde compound. Apart from this peak due to macromatic rearrangement, which is the M-1 signal or peak. So we call this peak a diagnostic peak for aldehyde mass spectrum. So you can always look out for this particular peak to know if a mass spectrum represents an aldehyde or not. For carboxylic acid, when carboxylic acid undergoes this macromatic rearrangement, they always produce a peak at 60. So this peak at 60 is particularly for carboxylic acid. Apart from this peak at 60, a mass spectrum, a carboxylic apart from this peak at 60 due to macromatic rearrangement, a mass spectrum of carboxylic acid will also contain a peak at N-17. And I'll explain what that implies. What that implies is that if the parent peak of a given mass spectrum is at, let's say, 100. So if the mass spectrum represents a carboxylic acid, we expect that there should also be a peak at 83, because 100 minus 17 will give us 83. So in carboxylic acid mass spectrum, there will be a peak at what? At N minus 17 signal will be present in the mass spectrum that represents a carboxylic acid. And the last but not the least, in this particular video I'm talking about, is the methyl ester. So note that there are different compounds under esters, but basically in this case I'm going to be focusing on methyl ester. So for methyl esters undergoing macromatic rearrangement, you can always see a prominent peak at 74. And also for methyl esters, you will also see N-31 signal, which implies that if I have a parent peak at 100 in my mass spectrum, if that mass spectrum represents a methyl ester, I expect that there will also be a peak at 69, which represents the N-31 peak. So please note that this M in this case is the molecular ion peak or the parent peak. So in a spectrum for methyl esters, we will have a prominent peak at 74 due to macromatic rearrangement, and we are also going to have a peak at N-31 due to removal of methyl oxide from the methyl ester. A mass spectrum can also represent a nitrogen containing compound or a aromatic ring containing compound. In a mass spectrum that represents a nitrogen containing compound, the molecular ion peak will have an odd number value, while in every other case, as I mentioned earlier, the molecular ion peak or the parent peak will have an even number value. So it is only in a mass spectrum that represents a nitrogen containing compound that you will have the parent peak having an odd numbered value. For aromatic ring containing compound, the mass spectrum that represents such compound usually have a bromine peak at 77, which usually represents a phenyl ion, and that is also how to identify those two class of organic compound. With all of these things I've mentioned, I believe that at this point you should be able to read a mass spectrum and identify what class of organic compound is represented by any given mass spectrum. To round this lesson off, I will also want to reinstate the benefits of the parent peak in knowing the molecular formula of the compound identified in a particular mass spectrum. So, for example, if molecular ion peak in a mass spectrum is at 100, so this molecular peak or parent peak is at 100, which is even numbered value. So what that implies is that the molecular mass of the compound represented by that particular mass spectrum is also equals to 100. And that goes back to what I said earlier, in that the mass to charge ratio of the molecular ion and the molecule itself is always the same. So let's now say for the given mass spectrum, I identify that mass spectrum to represent a straight chain alkane. For a straight chain alkane, generally, the general formula for a straight chain alkane is CnH2n plus 2. If this is the general formula for straight chain alkane, and I already know the molecular mass of the compound from the given mass spectrum, I will say that this CnH2n plus 2 will be equals to 100, and that implies that the next thing for me to do is to find this n. So, and that's by saying that 12 times n, where 12 is the atomic mass of carbon, plus 1, which is the atomic mass of hydrogen, times 2n plus 2 will be equals to 100. From this place, I will have that 12n plus 2n plus 2 equals to 100, and that means that 14n equals to 98. If this is further solved, we will get that n will be equals to 7. And with this value I've gotten now, I can now determine or know the molecular formula of the compound represented by the mass spectrum, which I have identified to be a straight chain alkane, and that it has a molecular mass of 100. Therefore, the molecular formula of the compound represented by the given mass spectrum would be C7H16, because we have our n is 7, that is C7. 2 times 7 plus 2 is what? Is 16. That will have C7H16, which is our heptane. And this is the way to use the molecular ion peak to know the molar mass of the compound represented by any given mass spectrum, together with the general formula of that particular of the compound you identify the mass spectrum to represent. So using those two things, the molecular ion peak value and the general formula of the compound you identify the mass spectrum to represent, you can get the molecular formula of the compound represented by the given mass spectrum. At this point, I want to believe that you have gained knowledge and understanding on how to identify the class of organic compound represented by any given mass spectrum. But if you are having questions or doubts in your mind, you can do well to drop that in the comment section. I really want to appreciate you for watching this video and for staying tuned. And I also want to urge you not to forget to subscribe to this channel. At the same time, share the link to this channel with your friends, that this lesson can also be helpful to them. Together with you and I, we can make this channel great and even better. So I urge you not just to watch the video but also to subscribe, and I will also welcome any question, suggestion and even comment that can be helpful for myself and even to move this channel forward. Thank you for watching and don't forget to subscribe.